Okay, so the goal today is to talk about these two results. So, okay, yesterday we left at a point where I said that in an atomic selfish routing network, the price of anarchy can be 5 by 2, right? So, and it turns out that there can be multiple, you were given an example. We can have multiple equilibrium flows and they can have a different values. That's the most important. I mean, that's the critical thing, that they can have different values. And the example was via a network such as this. Did anybody try? Did anybody work this out? Example. This is a very simple example, so it doesn't require. Yeah. So this was this thing, and I. This is if you try it. This has two equilibrium. Using one hop path and the one using two hop paths. And their values can actually be different. And it turns out, I've worked out this example. Okay, so let's say paths and yeah, so one for both cases for all of these agents, we are using 1 unit of traffic and two hop paths and different length. And POA is basically 2. So do you all want to see this or should we move along? Are you all saying something?
We can move along.
Fine. Okay. So the point is that each one can be, so they can have different equilibrium flows. But when we say POA, which means the worst cost equilibrium, by the optimum or minimum cost flow. This is 5 by 2. Okay. And there's a theorem which, again, this theorem is quite similar to what we have done before, what we have seen before, the last two theorems that we saw, where we show that I forgot who actually proved this theorem, but in every atomic selfish routing network with affine cost function. Okay, so affine cost functions are almost linear. It's like something very similar to linear, but not exactly linear, because you have this cost function has this appearance of ax plus b. With affine cost functions, the POA is at most 5 by 10. Okay. All right. So, um, okay. So so how should we begin proving? I mean, in a way, it's not surprising. It's all these are similar. This sort of technique, the common thing where we take a equilibrium flow and an optimal flow and so on and so forth, and compare and do that hybrid cost thing where basically we use the cost associated with the equilibrium flow and freeze it sort of as if that's a constant cost, and now pass optimum amount of units of flow. That's what I guess in literature they call it canonical congestion flow or POA type arguments. Okay, so it's a natural way to sort of see how what is the optimum flow doing that the equilibrium flow is not doing, and so on and so forth, and then getting that weird that hybrid quantity, right, as like a in between quantity, and then using that to compare it to the optimum flow. So that's the general idea. Okay, so affine cost function would be, let's say, um, define it. I wrote all these things yesterday, but let's see. C of x is this, where all a and b are greater than or equal to 0. Okay, so this is what an affine cost this thing means. Okay, so let's see. First step is as before. F is let f be an equilibrium flow. Okay, this was also, now that I remember, this was also something that I left the optimum flow. Okay, we can have multiple optimum flow, that's all, let's say. So this also I left you guys. So you all should really dictate to me as to how to do this. Then what happens? So how do we define, oh, and yeah, so in the atomic gravity network situation, how do we define flow? Quickly, we have a few things we want to do today. Tell me.
There are so many paths to choose from, and each agent chooses one of the paths, and flow of one is routed for that agent in that path.
Yeah. So as opposed to some choice of path, right? K being the number of agents. Pi being from the feasible path choices for agent I, because agent I wants to go from source I to target Ti. Correct? Okay. So F star also has something similar. It's again a selection of paths, nothing, let's say, so on. Okay. So now what do we do? So yeah, this is okay. Then
In the previous proof, we used that all equilibrium flows have the same cost, and
but Sanjay, that is not the case with in this case, right? We saw that this is what this example will show, that you can have multiple equilibrium flows here. So over here, so we have to use the definition of equilibrium flow. See, that day's lecture, when we said that all equilibrium flows have the same value, we didn't prove that. We will see the proof today. I said that as a fact, just assume it for now, and then we will see later on. The fact I assumed it then so as to just define the price of anarchy as the cost of any equilibrium flow divided by the optimum flow. Right? If you have multiple cost flows, then the point is the price of anarchy would be defined as the worst equilibrium flow divided by the optimum flow, right? So that's the thing. So over here, so I can't assume that there is a unique. I mean, I can't even assume that all the equilibrium flows have the same value, let alone there's yeah. So let alone a unique one and so on. So let's use the definition of equilibrium, right? What is the definition of equilibrium flow? If F is an equilibrium flow and F star is not, then F star need not be. F star is anything, then I can say for each agent, each agent, right? I know that the cost it incurs under F is no worse than the cost it incurs under F star. Right? That's the definition at least I have. So this agent chooses PI. So the cost of this thing is less than the cost he incurs under F star. Correct?
We defined it as just one person changing the path.
You're right.
So
Okay. That's right. You're right. So you're right. So this is not actually the sorry. That's another thing. So what we can say is for this agent I, his choice in this flow F is no worse than if he alone deviated to pi hat, whatever pi hat is in this flow. Correct? Okay. So how do I write that expression? Deviation, let me write deviation by I to unilateral deviation to pi hat, cost, rather cost which is equal to what? This CE, let's say, that is intersection, PI intersection, PI hat, CE, FE, plus the cost due to the new edges. Correct? Good. Yeah. Okay. So now, using this, how do we sort of extract the kind of bound that we need, complete the analysis for this 5/2 bound? So okay, so I should just write this down here. See, this thing is equal to somehow the it's not working. This is equal to this. Okay, this quantity is this quantity is this. Correct? Okay. So now, so we have a bound just exactly like the way we did this first time. We have a bound here, upper bound of the cost of the equilibrium flow. So what was the part? Yes.
So CPI of if the subscript under the summation should be summation of E in PI,
Sorry.
Okay.
Sorry. Yeah. So this was the first step. We have the upper bound. Like then, now what do we do? Now we do this sort of a hybrid sort of freezing of the cost and so on, right? But now something. Okay. So using this, and so we are saying this about each agent type, right? So now I can sum this up across all the agents, and still the summation would hold, right? There's nothing new here, right? This quantity.
In the sum, the PI hat should be chosen appropriately for each
Yeah, but
agent
I'm
type.
saying PI, okay, but I'm saying symbolically, I basically just have to put this here. This PI hat is, by definition, PI hat is the chosen, the path adopted by agent I in this optimum flow,
All right.
right? So that way, okay, I just like it's too much of a long expression, so I don't want to write. All I'm saying is, given that this relation holds for individual agents, it will also hold in on an aggregate, right? That's all. Okay. So basically, this tells me I get a summation. I mean, I get a total. Small is a bit. Yeah, you have to pardon me this horrible cracker thing. It will happen probably. It's almost evening time, so yeah. All right. So this left hand side is this quantity is cost of f, right? Nothing more. This right hand side is what? Do we have a physical interpretation of it? It's basically the total cost incurred by everybody due to the unilateral deviation of one person, right? That's it, nothing more. The total cost due to the unilateral deviation. So it's like F minus. This is like the cost of, let's say, cost of F minus I hat pi. Correct? This is our notation from the classical, this thing, right? From previous lecture, f of minus I, whatever this was, f, and just replace it with one agent's unilateral derivation. Okay. So now, what can we say? Can I get a useful bound using this? The fact that fe plus 1, so okay, we know that the cost of this cost function ce is a non-decreasing function, right? You can think of it as like this sort of thing. So instead of this cefe, I can basically replace these terms by a quantity which is cefe plus 1, and I can only get an upper bound. So this thing. I should have a summation here. We need to have it. Okay, let's have it. Is this okay? All I did was replace all of the, so see over here, we have a summation which is additive over two terms. One is those edges which are in the intersection of pi and pi hat, right? And this is pi hat minus pi. Either way, both these cases, both these terms correspond to edges that are in pi hat. Now this value is smaller, at least no bigger than this kind of a value, because CE is basically a non-increasing function, non-decreasing function, right? So I'm just going to write because CE is non-decreasing. Okay. So as I said, it's all a bit algebraic, and but okay, this is the way it is. So we at least know that the cost of f cannot be more than this, right? Now what? How do I like sort of usefully transform this entire expression into some a bound that I can use to infer my final result?
This will be Fe is summation over edges Fe into C of Fe plus 1.
Will
And
it
we
be
should get cost
Fe?
of
Will it be Fe or will it be Fe star?
Fe star.
Yes, and why is Fe star? Because of this, right? Because we are, what are pi hats? These are the choices that Fe star made, right? So that's the thing. Okay. Otherwise, pi hat is not even in question. Pi hat is just only chosen by Fe star. So this is the thing. Okay. So perhaps I should have, instead of saying Fe star, I should call it Fe hat. Okay, whatever. Star is the E times CE FE plus 1. Correct? Because adding across all edges. Okay, this should be this thing. Sorry. This summation now changes to this. Okay. Yeah. Edges used in F star. Okay, correct? This. See this and then this. Okay. All right, shifting a little bit. Now what? Are we done? Used in F star by, say used, I mean by all agent to get. Okay. Yeah. So now what? Now we are almost done. What do we have? Do we have anything else to say? Remember what? So basically, okay, we are only claiming the result about the affine cost functions. So the affine cost functions should be used somewhere, right? So basically that 5/2 bound holds for affine cost functions. When you don't have affine, you can show that this POA can be worse and so on, okay? So therefore now I'm actually, there's not anything else. So basically now apply the definition of the affine cost function, okay? So what was it? Ax plus b, right? Okay. So we should not use ax plus b. It could be every. So remember, when we say that the function can be affine, what we mean is the cost function on the edges of this network has affine nature, not that they have the exact same affine function. Correct? So this is why I'm going to now index the cost function by something AE. Okay. So what should I say? FE plus 1 plus BE. Correct? Where CEX is, let's say, AEX plus BE. So what this means is that um, AE and BE as constants can vary edge to edge. Okay. Okay. So now Now what?
We saw the bound and product of two numbers yesterday, right?
Yes, exactly. This is the sort of thing. Sometimes we kind of have to know some. Okay. So see, the point is right now what we have is we kind of started with this path description of it, what was happening path by path, like in terms of deviation, and then we have sort of whittled it down to accounting for the cost or the congestion experienced edgewise, because that's where the congestion comes in, right? When I'm traveling on a path, how my time gets delayed edge by edge, that's where my cost sorts of adds up. So basically what we have done is we have analyzed this equation expression as much as possible down all the way to this edge. Now we kind of have to use some property about the cost function itself vis-a-vis this f star e and analyze it. Okay, so that's the point here. So now using that lemma, we de-entangle it, I guess, for every y, z, y into z plus 1 is less than equal to 5 by 3y squared, 1 by z squared. So see this, so pay attention to this is y squared and this is z squared, okay? And this is the thing. I have once applied this incorrectly, like I sort of this lost track and yeah, okay. So now how do we apply? Applying this lemma to, let's call it star. What do we get, guys? Oh, sorry, Satya, you were saying something. You can't speak up, dear. Yes, we do give bound edge by. Satya, your messages only I can read. Perhaps you can send change it to everyone, then everybody can see. And they might be able to point out if you have a message. It's no point writing. So plus 1 is less than equal to. Yes. So how? Why I copied this one? I just wanted to copy this. So instead of AE and here instead of AE we have Y and so on. So F star E 5 by 3 AE squared, right? Please check as I'm writing, please check if I'm writing correctly. Plus 1 by 3 FE star plus BE. Is this correct? Right? So
Yeah.
A is Y, right? Y square and Z, oh sorry, Z is my FE. So 1/3 FE square and plus BE, right? All right. So now anything looks familiar or something? What? Wait, I have a different bound one. Wait, F star A. Am I? It's wait. Why it's important? I have made this mistake before. So this is correct. Let me just check my memo. Why? So this is F star E. A E F E plus 1. Oh, correct. You know what? Okay. Sort of just, I think it makes a difference. Okay. So I'm not going to apply it on this. I made this mistake once before. I'm going to open up this and combine this. Fe star, Fe plus 1 plus Be F star. Okay. This is the expression on which I will apply the lemma. So weird. I worked out the details and still managed to make a mess. To start, we get, now tell me, cost of star. So this is now, this is this y, this is not this expression is the y into z plus 1, okay? Y is f star e is less than equal to ae 5/3 f star e plus f e plus b e f star e. Okay, and of course this will all add over here. Is this correct now? I don't think so.
Is the term multiplied with 1/3 squared of 50 or
Yeah, fe star. Okay. All right. So now I can do 5/3 summation e. This is f star e square plus be f star e. I could have taken f star e common, but 1/3 ae f e star. Okay. Yes. All right. Let's try to move something. Okay. So now,
I have a doubt here. So the B F E star's coefficient is 1 in the first term And now it is multiplied by 5 by 3. Should we subtract? It will make
Um, okay, less than equal to 5 by 3 is more than 1, right? I need this sort of common out here. Okay, now what? Do we now have a familiar? Okay, let's just take this a little bit more.
cost of fees.
Yeah, let's just take this thing common out. A. It will look when massaged carefully at this sort of thing, it sort of starts to look a certain way, which is this. See, now that's 1/3. All I did was just AE, right? So this term now, let's just sorry, this term, rather not the summation even. What does this term look like? This is basically optimum flow cost along the edge, right? So this was the whole point of doing all this. So let's write. I can just replace it with just cost of F star. Right? Yeah. 1/3. And what is this? AEFE star? FE square, rather. What? I can always add plus 1/3 B. I can always add this and this will become less than equal to. Right, okay.
Equilibrium flow.
Yeah, but to interpret like this, I do need this plus term, right? This additional term. But then the equal to should become less than equal to because this is a positive quantity. So this is why, see, it is crucially needed for me to have BE to be positive. All these addition and all this sort of many of these things will these things will simply not hold if the cost function is it does not have the non-decreasing property, or this affine this AEBE quantities are, these coefficients are not positive and so on, right? So this is why this. Okay, so now this is cost of F, correct? All right, now left hand side I was already carrying this cost of F to be this. Therefore, C of F is less than equal to 5/3 C of F star minus plus 1/3 C of F. So basically 2/3 C of F is less than equal to 5/3 C of F star. And voila, we have our bound that the cost of an equilibrium flow can be at most 5/2 the cost of F star, which means that POA can be at most 5/2, right? Okay, so QED. Okay, so do you have any questions about this analysis? Yeah. So this is the sort of the type of analysis we have now seen, like 3 proofs, right? The first one, second, and then this thing, this hybrid kind of thing. Okay, so now let's move to this yeah, existence. This I think is the most of PNE. Okay. selfish routing networks. Okay. Okay. Uh, so we have seen that I have said this before, and I mean, you recall from yesterday, I'm sure, that we always know that mixed strategy Nash equilibria exists for finite games, right? My question to you, is this a finite game? Can I envision the selfish routing network to be a finite game? Because if it is, then we can at least say that there's a mixed strategy Nash equilibrium, right? Now, and then the question becomes relevant whether there exists pure strategy Nash equilibria and so on and so forth, right? Okay, so at least let's figure out, is it a finite game?
The number of, I mean, the graph is finite, so the number of paths is also finite.
Yeah, that's basically the point. Okay. At the very least, for the atomic, so the thing is, for the atomic games, at least, where it's really you're passing one unit of flow, and one unit, everybody is passing one unit of flow, and basically players have to choose paths. So their strategy space is finite, and there are finite number of players. Therefore, that defines a finite game, correct? But when it comes to the non-atomic, yes. So the Satya is also saying this. In the non-atomic setting, we don't really have a precise notion of a player, right? We are saying that the unit R has to be split among the paths on the graph, among the S to T parts of the graph, correct? And how we split it, how much edges we have it, and so on and so forth. The splitting as such does not have, it can be fractional and so on and so forth. So it's not clear to me from that description, at least, whether it's a finite game or not. But is it, do you think it's a finite game, the atomic, non-atomic setting?
We should define who are the players.
Okay.
What is that?
The point is that we don't have an explicit notion of a player. That's the whole point of a non-atomic game, right? But so then, yeah, there's no explicit notion of a player. You can think, I don't think it, so, because the word player doesn't make sense if we can't sort of, the player comes with a few a few attributes, like it has to have a strategy space and the clearly defined payoff type of, or a cost function or utility function and these sorts of things, right? So over here, so yeah, for non-atomic games, at least, it's not clear to me how to think of it in the standard terms of players and this sort of thing, and finite games and so on. Okay. Fine. So the proof of why there exists a pure strategy Nash equilibrium. Now we said existence of pure strategy Nash equilibrium in this thing. Within this, I'll just write this makes the definition of POA meaningful. The way we have been defining so far, right? The POA is being cost of worst equilibrium. Otherwise, if there's no equilibrium, then the notion of worst versus anything does not make sense. Okay. No. Correct. Okay. All right. So this is a theorem. How are we doing time-wise? Don't want to keep you all wait too much because okay. Every atomic selfish routing network, my belief is that Rosenthal proved it for atomic selfish routing network, and later on it was extended to non-atomic settings also. Okay, so I'll make some comments regarding that, but this is the version that's attributed Rosenthal with arbitrary real valued function has at least one equilibrium flow. Okay. So we are not talking about only affine cost, linear, nothing. We are talking about arbitrary real valued cost functions. Okay. All right. So proof. The point is via this notion of potential. These are very special category of games where um, the the way the game is played, the strategy, the actions of the players, and so on, it collectively becomes as though the players are together trying to sort of minimize some potential function. So optimize. I should not say minimize. I should say optimize a potential function. Okay. So what is that potential function? So let's define. For this game, this is how we define the potential function. Okay. There are other games which also are potential games. There, the potential function may be defined differently. Okay. Tell me, I'm going to write it here. Okay. I think yesterday, Satya, yesterday when I asked you this question, you said that the potential function should intuitively try to capture this object. Should try to capture the effect of unilateral deviation, right? So can you explain? Can you give some idea what that? So then, how do we define a potential function? That's a correct intuition. Okay. So tell me, I'm writing here. Tell me if this sort of makes sense. Okay. So this box I means I starts from 1, 2, 3, 4 and goes all the way to f of e. Okay. The flow sent through this edge under this flow f. All right. The traffic sent through this thing. Again, we are talking about atomic selfish routing network. So f is a choice of the paths p1 to pk, and we define this function phi of f to be this. Okay. Yes. Tell me, can you interpret in a sort of a meaningful way this quantity? And more so, do you think this captures what we were discussing there? That is,
Could you please repeat what is there under this inner sum I in set?
oh, okay, then maybe I write it. So I is from 1 to fe. So, okay. So you recall f of e was what? F of e is number of players who have chosen players that have chosen paths that contain
Okay.
e, right? So fe is necessarily an integer. So this I is going from 1 to f of e, and this is the quantity. Okay. All right. So basically, let's see an example. Suppose what is are we saying? Say Fe is what? Uh, oh, yeah. I don't know why this is so thick. It should not be. It's like. Okay, whatever. You understand this is supposed to be 1, 2. They're supposed to be of equal width, but okay. I can't draw it. So these are all right. And this is the cost function. Okay, right? So this is the CE of 4. By the way, in this situation, I have drawn a particular function which is increasing, and so again, but it's just only an example. Okay? So correct. Hmm? Okay. So we can do this. Hmm? So point is this: the two. This height is CE of 1. This whole height is CE of 2. This whole height is CE of 3, and this is CE of 4. Right? So basically, when we are looking at this quantity, C of 1 plus CE of 2 plus C of 3, we're looking this sort of stacked cost function, right? So in a way, if you think about like traffic on a network, on a path or so on and so forth, first, let's say there was just one car. Then there are 2 cars, right? 3 cars and 4. So this sort of the cost sort of adds up as more and more cars appear, correct? Okay. So in okay. So now can you say in this diagram, what does this quantity actually represent? Yes, Satya. It's the area under the curve. Why do you say less than?
We need the integral for the area.
It's the integral of this, meaning, yeah, that is what it is. Yes, area under the curve, and this in this case, whatever. So the integral captures the area under the curve, right? So yeah, but I'm saying, why do you say area under the curve? That is which, however we get the area under the curve. The point is, it's the area under the curve. Why do you say it's the area under the curve? So that you can't speak. Okay, so let me just. It is correct. It's the area under the curve. Okay, so let's just. Okay, I want to be able to draw this. So it's this portion. Oh, let's say now, if I were to compare this with this quantity, Fe times Ce of Fe, right? Which was what? Which was the cost associated or the delay cost associated with the same network, right? Same network, but non-atomic flow. What would that value be? What?
The last line is
Actually, sorry, see one thing, sorry. See one thing, this CE1 is basically CE1 times 1, right? 1 being the length of this. So CE1 is this thing, is it not? This area, not under the curve, just this thing, right? Yes or no? Okay. So let's say, similarly, this CE2 times, this is again, I'm assuming this there's a 1 multiplied here. What is this? I can think of it as this thing. I need less pale colors. No, not so. Right? CE3 would be similarly, no, this area. Hmm. And CE4 would be blue. Correct? Okay. Now, what is this? Now, you guys have to tell me what is this quantity?
A of the whole rectangle.
Yes, this whole rectangle, right? Right? So, in a way, this is the way it accounts. Why did it say recording failed to start? All right. So this is the way. So we can see this is how the way this atomic routing network accounts for the traffic delay, like this sort of slabs of delays, right? This way it sort of adds up. Whereas in the non-atomic setting, it's like this one big chunk, this sort of way. Okay. Now, so let's, what are we saying? Right. So let's go back to the intuition behind why did we define, why does phi of f work? For the purpose that we have defined, which is to say that there exists at least one equilibrium flow. So I claim that for any unilateral deviation from f to minus I, let's say, okay, where everybody remains the same except the ith player has changed. Let's have, sorry, we have phi of f hat minus phi of f is equal to C H. Sorry. It gets, let's see. P minus FE. I claim this is the case. Do you agree? Is it easy to see? See the definition of F hat. You can see the definition of F hat. So let's just prove it. Okay, but prior to this, suppose this were true. Why am I caring about this? Like, what would this give me? What? It would tell us that the difference between the potential function, right, from any flow to another flow where which is a unilateral deviation, right, is captured by this change in cost, right? Therefore, in particular, if F is an equilibrium flow, right, we know by definition an equilibrium flow is one where there should not be any improvement in cost, correct? So if I take a function f, if I take a flow which minimizes this quantity, then given that we have that property, this condition, will it not imply that f hat is actually that f, the one that minimizes this potential phi, is actually an equilibrium flow? Why? Suppose we take a flow, suppose we take a function f, right? Suppose it's true. We'll come back and prove it, okay? So let's, because we should see why we are proving something, okay? It's like, say this is true. We define f to be, not f, f, which is an argument f are all. Okay? Sanjay is very sleepy. Okay. This is this. Okay. You've had a heavy Diwali lunch. Okay. So I'm quickly, I'll just finish it in, 5 minutes. So suppose this is minimum. Okay. So what does that mean? For any other flow, f hat, right? We know f hat is greater than equal to this. By definition, right? I have chosen a f which is minimizing this phi function. So any other flow f hat should be at least as much as this, correct? But then this means what? F hat minus f of this is greater than equal to 0, correct? Yes. But, and what is this left by claim? This quantity is what? Is it not the increase in cost of this sort of the increase in cost due to agent I moving to this path pi hat instead of pi? If this is positive quantity, if this left and right hand side is a positive quantity, it would tell me the increase in cost, right? Because the agent has moved from pi hat. He was originally in pi and now has moved to pi hat. That's what this one gives, right? If this is a positive quantity, it means this quantity is bigger than this quantity, right? So it means that he has incurred an increase in cost for shifting to pi hat, right? Yes or no? Therefore, by claim, this would mean that how do I say this? Okay. This is true. For any flow, this is true. In particular, for any flow 4 hat, in particular, true for f hat, which is a unilateral deviation. Unilateral deviation means exactly one agent is changing, right? So by claim, left-hand side is equal to the change, increase in cost. Just a minute. One second. One. So, change in cost for that agent deviation. If change in cost is positive, it means it's the opposite of an improvement, right? I mean, that it means F is actually a meaning if anybody deviates to something else, they are having an increase in cost. It means that F is actually a equilibrium. Right? Yeah. Okay, right? And so we would have it. Now, so let's just prove what the claim is. Okay. So you're convinced that proving at least this claim will sort of end our entire theorem, like it will complete the proof of a theorem, right? Okay. So tell me, why is this? What is the? How do we prove this claim? Just look at this and so quickly. So tell me. See, it just follows from definition. Phi f hat minus phi of f was what? If you apply the cost function definition, it is just, it was like this, right? E of e, f I in f of e, this is f hat, let's say, ce of f hat e minus the same thing, right? We can write ce of f of e. So it's not f of e, sorry. Sorry. The index I going to, right? Yes. So what is the difference here? The only all those paths, or rather all those edges which are unaffected by the deviation of this person, right, of the agent I, all those paths remain unaffected, meaning all those edges where no new flow comes through, they are unaffected, right? So their quantity from this thing and this remains the same. So Fe is actually equal to F hat E. So that gets cancelled. So the only edges remaining are what? So we can think of only edges whose difference matter. Yes, tell me, what is it? The only people who will see a difference here, the only terms that will survive are the terms for the edges that are in the symmetric difference of pi and pi hat. Meaning edges that are both in this portion, the edges that are unaffected due to the deviation, they are exactly the same. The only people who are the edges that are affected by the deviation are which? Those that are in pi hat but were not in pi, they will see an increased load. And those edges which were in pi but not in pi hat, right? They have something shifting, right? They will see a decrease. So for them, the situation changes and those terms will survive here. Okay, let me just write this and then you tell me. Into pi hat minus pi ce f e plus 1 minus ce, sorry, e, which is pi minus pi hat remains at f e. Sanjay, you're inaudible.
Could you please show the claim statement once?
Yeah.
Okay.
Okay. We are only talking about that. So phi of f is defined with respect to every function f. But in particular, if we look at function f, if we fix a flow f and look at a unilateral deviation flow f hat,
Yeah.
then we see the difference between phi of f hat and phi of f, then we get this quantity.
Okay.
For only this, we are actually talking about. If multiple people change their flows and so on and so forth, then of course this term cannot be this clean. Then you have to account for all the agents, like, sort of confluence of flows, like how blah, blah, blah.
Yeah.
The fact that it's one agent, unilateral deviation, so this becomes neat. But the point is, do you see how these terms get cancelled? In particular, I is ranging from 1 to all the way up to f hat of e. Over here, I ranges from 1 to all the way to fe. After the deviation, either f hat of e, right? F hat of e could have risen because of the newer, this, like on an edge e, if new flow is coming through, then basically it whatever was there before already remains. Extra 1 unit is coming through now, extra, right? Yes or no? Once when you have a deviation and if the situation is on an edge, extra 1 single extra unit of flow is coming, right? Initially it was behaving the way it was in pi and now 1 extra unit is coming. Here is the term which was happening before deviation. Therefore this term and this term will cancel all the lower terms of this, and the only term remaining from here would be the augmented term, which is what this is. Correct? And similarly, the same logic applies here. Terms here will cancel out terms here, except that the last order term, that the one remains, which was in pi but not in pi hat, right? There's no way to, like, there's a reduction in pi hat, therefore this term remains. Okay, so convince yourself. This is sort of, again, it's visually, I think, much more easier, or whatever, intuitively it's probably easier to explain to oneself than maybe to other people. Okay, all right, so now what, quickly? So if this is the case, now remember we have to show what? This is the right hand side, right? This is exactly the definition of the right hand side. So all I have to do is add the intersection terms, right? Just add pi hat intersection pi. And then this term. This minus CE. FE. Yes or no?
Yes.
I mean, I don't even have to think of, sorry, this is not, this exactly, this is just FE. I mean, literally this plus minus is the term that cancelled out, right? So, but to get the closed order term, we can think of it as this way. And this and so on. Correct? So this is basically equal to nothing but I just take together all the edges in y hat and say this is equal to f hat of E minus edges of I, which is CE of FE, right? This captures the entire expression of what is happening under f hat of E. And this term, whatever this is, CE, this is this term. Right? Yeah. It's a lot of stuff. Not star, maybe. Yes. Okay. Okay. All right. So what's to do next? So ask me any questions if that you might have. I am not going to, okay, I should just say something more. Just one more term, one more this thing. This was about, and claim is okay. So this is about atomic selfish routing network. We can extend this idea above to non-atomic games as well. Can you tell me how?
When you say extend, what do you want to extend?
That there exists a potential function, meaning this that even for non-atomic games, you can show that there exists at least one equilibrium. So I have told you that one way we have actually proved shown a proof technique to show for some games that there exists an equilibrium, right? One way to is to exhibit a potential function and thereby prove that there's a potential game. This is a potential game. And then by this kind of analysis, by the way, over here, notice something. I did not assume anything, any property about the cost functions. CE could be anything. No, I did not assume it was non-decreasing, continuous, blah, blah, none of this, right? This is just some terms got cancelled and so on and so forth simply because the same object appeared somewhere. We use none of the other properties of the cost function that we used in the POA proofs, right? So this analysis is actually very generic, this sort of a thing. So my point is this idea can be extended to a larger class of games as long as we can exhibit a potential function. Okay.
in the previous, here we had this potential function and showed that show how it relates to the notion of equilibrium in this game. So there we need to define some potential function and show that the notion of that equilibrium is captured where
Yes,
minimum path is chosen.
yes, exactly. So, um, can you tell me how to do this? In particular, see, one thing is there here when we define the potential function, right? Um, don't really know how to. Okay. Um, we are not over here when we define the potential function, we are not really making an explicit mention of any of the individual players, but the primary difference between a non-atomic and the atomic game scenario is that in the atomic game scenarios each player has non-negligible sort of control over the traffic and the way the congestion builds up, right? And in the non-atomic setting it does not have. But even though it is not explicitly mentioned there as in the formula, but in we can basically replace games by defining this way. I have taught this proof in one of the classes before, this more general this thing. It's not complicated or anything. I mean, it's just an area under the curve type quantity. So over there, this quantity was this thing, right? This summation. I going 1 to f of e, c e of I, correct? Here, the reason here it works this way is because every player who chooses, the moment even one, the first player to think of the congestion on the edge building up. I first came into the road. Okay, it's like my car is waiting. Then some other player comes in who also chooses a road which uses this edge. So the second car comes in. Then the third car comes in and so on. How many such cars build up? Total number of players who actually choose paths that use this edge. Okay, that is what the final CE of FE basically represents. Okay, it's like the congestion is building up for the first time. When first car was C, it would have been CE of 1, then CE of 2, then CE of 3, and so on and so forth. That stack diagram, think of this. Whereas this, no play. And by the way, we are crucially assuming that when a player decides to use a path and therefore and all the edges on the path, it is routing all the one whole single unit of flow through it. This is why we can, the number of players who choose the path is equal to the total load on that edge. The number of players who choose a path that contains an edge E is basically quantifying the total amount of traffic on that edge, right? But in non-atomic games, that's not the case. There's like one player who, think of it as like one player who is, one player or infinite player, whatever. They are just sort of splitting the flow across the network, right? In that case, the amount of difference that we have is infinitesimally small, the x this thing, and the natural way of capturing such situation is by integration, right? So this is the thing. So this is the sort of a compare and contrast as to how this formula generalizes to this for this sort of a non-atomic game scenario. Okay, now where, okay, I should write here, um, here where f is, sorry, is amount of traffic, correct? Not the number of players who are using. This is versus this thing in atomic surface routing networks, and F is number of players choosing paths containing E. E on path on E. Okay. Now, also, moreover, atomic games, non-atomic games, we assumed that the cost functions are, you remember what the definition, this is where this becomes essential. The cost function being, they were continuous, non-decreasing, and what else? There was something else, but this is essential. This being continuous and non-decreasing makes, see, non-atomic surface charge. Oh, I think I had also said non-negative. Yeah. Okay. But yes, this is continuous and non-negative. The function phi f as star is continuously differentiable, and these things are needed to show differentiable. For the entire calculus proof to go through, where we get to the same conclusion that the function phi has a minimizer, and that minimizer gives you an equilibrium flow. You need these sorts of salient, these things play a role there. Okay, so convex. Okay, so using this idea and few more, uh, we can conclude that the local minima phi is an equilibrium flow. Okay. Um, Uniqueness, right? This is the thing. Okay. Uniqueness follows from what condition of the minima? Tell me. Can you say why it follows? Okay, I've already written the local minima of phi is an equilibrium flow. You can use these things and sort of show it, let's say. Suppose it's true. What can I say about the global minima? Anybody? Can you use the property of convexity of phi? What? So each of the local minima are the global are equilibrium, right? That's what I'm claiming. Uh, I don't know. Okay, so let's say try, okay, we don't, convexity of phi implies that the local minima is the global minima. And thus, therefore, this equilibrium. So you don't have different equilibrium values, basically, is the point. Okay. So the
Can you
global minima of the flow of global, so all the local minima are equilibrium flows. Now, if you have a global minima, right, what would that mean? What is a global minima in this context mean? It's the best of the equilibrium flows. Correct? Due to the convexity, we can show that the local minima is also a global minima. And therefore, it is unique. Okay? So, let's follow this. Yeah, the above proofs were more algebraic. This is a bit more calculus, maybe, and so on. So, try to show this on your own. Okay, you should. Unless you have, do you all have a question? And if I mean, I'm done teaching for this portion. So unless you all have a question, I've basically done. So my suggestion to all of you would be to prove these things on your own. You know enough about calculus. These require basic calculus. Notions of sort of differentiable, what functions are differentiable, what convexity means, and so on. And maybe a one or two elementary, like open a calculus book or rail analysis book, and these results are very standard there. Okay. So using that, we can show all these properties. And so that sort of ends my sort of part of the teaching for the congestion games. Now, okay, I've been talking about selfish routing network and congestion network almost as sort of interchangeably, but there is a precise no definition of congestion games. Congestion games are basically one where you have a graph G, okay? And it's a generalization of this atomic selfish routing, this thing. So resources are like edges of this graph G. Okay. Each player, let's say there are, has strategy, which corresponds to some subset of the edge set of the graph. Okay. Basically, it can use a subset of the edges. Okay. Okay, let's write it this way. Each player's, this is this. Okay. No, I don't mean that. I mean subset of collection of parts. That's what I mean. I don't mean some. Yeah, I want to write it this way. I has collection of parts it can use. Yes. Okay. Now, this is the setting of congestion games. Okay. And of course, you have cost functions associated with it. Cost function associated with edges. This is what a general congestion game. This is what a congestion game is. So it's basically a type of a selfish routing network. Do you see any difference between what this is versus what that is? What we have been talking about? This here, right? This is basically this subset of edges, subset of this thing. Previously, we were only considering some specific SI to TI paths. So here it can be a lot more general. It's like I can clog up an edge just like that as an agent. Okay, it's not necessarily on paths and so on. Okay, so these results extend to congestion games for more this sort of a general class of games. but I don't know if we'll see it towards the end of the course. I mean, maybe after the course we have some extra lessons and so on, and that in that we do it.